on how an interactive agent can help you learn how to solve Rubik's Cube fast in an efficient manner. Subsequently, in the food domain, where we have trained conversational systems that can allow you to interact with the system in a way that where you can define you can receive food recommendations, keeping your allergy specific constraints into account. In today's tutorial, we will be focusing specifically on the conversational AI in the healthcare space. So let's just start from the very basic on how do we build such a conversational agent. We take off-the-shelf transformer models because they are the current state of the art. We give it a series of large-scale textual data in the conversational domain, and these are like the questions and answer pairs, and you train it over the weeks of your training, which ends up giving you a trained generative model that can allow a system that's actually being brought into the system for the conversations. You use this generated system to facilitate a conversation with the user. Essentially, what happens is that when we try to utilize, when we employ such a conversational system, a generator system into a very domain-specific use case of mental health care, for instance, we see that the generated questions by the system are not safe. For instance, in this case where the agent asks the user, do you feel nervous? The person asks with more than half the days, and simply using the off-the-shelf parametric knowledge, the knowledge that it has gained through large-scale training over the conversational data, it ends up generating these questions. And if you pick the second question, for instance, is do you feel something extreme might happen to you? It sounds risky, and it has a negative connotation associated with it. Most importantly, such questions would not be asked by the user or by the agent, or it should not. These questions would not be asked by the clinician itself in a clinical setting. So how do we keeping this idea in mind that there is an unsafe question generation possibilities, we looked at the large scale language models that have been built over the time, and we found that most of the studies have been focused on how these language models generate factually incorrect responses, and how they are generating questions that aren't safe. Up to the recent Google's Lambda model that talks about how we can utilize Google's long list of safety guidelines to place constraints on safety when an agent is interacting with a user. On the parallel line of this process of using safety guidelines, we introduce the concept of safety checks. This safety checks are a very simple scenario of putting a constraint when the model is generating these questions. These safety checks are like in the current generated question by the agent, we want to check how many of these terms that are being used in the generated questions intersect with the safety lexicon. And subsequently, we want to check that the representation of this generated question matches some of the representation of the questions that are being proved to be medically valid and safe and are documented in a medical questionnaires. So as a consequence, some of the generated questions that the model will yield to the user would be medically valid and safe. So this was a simple safety checks that we introduced into the generative processes, which resulted into a significant improvement in the performance of the model, which is manifested in the reduction in the number of generated questions which are unsafe. We saw that this was a magnificent decline of 65% that we saw by this knowledge infusion. This infusion, which we call as knowledge infusion, is about the constraints that are being introduced before the model is able to generate an outcome. Let's look at some examples of it as well. Now, if you see on the left is a generated question coming out from an attention model, which has been trained on a large scale conversational data. And if a question that comes to the model about a person's displeasure of doing anything, the model comes out with these questions. And if you look at these three questions, then you see that such a question should not be generated from an agent. Essentially, what we did was we checked these questions' similarity with some of the known lexical resources as well as semantic resources in the depression domain. We say that these are the similarity scores that we achieve by these questions. And most of these similarity scores, if you see, are around the terms do you feel and your levels, and not exactly the terms like risky behaviors or brain or dopamine, because those are terms which do not occur in these questions. However, on the other hand, when we looked at the knowledge-infused attention model that I showed you, that I just highlighted in the previous slide, we said that the similarity scores are significantly higher. Most importantly, because here the generated questions are covering the phrases, are taking the phrases into account. For example, lack of pleasure is least pleasure are very much similar. They're probably, that's a good concept to ask the user, is he having a lack of pleasure, and what he means by lack of pleasure. And then the subsequent questions are in entailment order to the previous questions, and subsequently and so on and so forth. So these set of information sources like DSM-5, PHQ-9, and SCID, which is a structured clinical interview for depression, you can actually introduce a particular order in which these questions needs to are to be generated. And we kind of looked at the similarity scores between these questions and these lexicons, which came out to be pretty high compared to the one generated by the model without knowledge infusion. Under the hood of this behavior is a simple process. What we did was, in this safety checks, we kind of introduced this constraint. This constraint is nothing but a process. We checks that if the previous generated question of the model, assuming that the previous generated question was acceptable, was about the cause, then the current question generated should be about the symptoms. If the previous question was about the symptoms, then the current question needs to be about the medications, and so on and so forth. So essentially what you are looking here is that you are having a lexicon, assuming in a very simplistic scenario, that defines what are the causes of depression, what are the symptoms of depressions, what are the medications of depression, and what are the treatment that the clinician offer to the patient when he's suffering from depressions. And essentially your model is learning is that taking these lexical cues and computing the questions that can be generated. So rather than blindly generating questions based on the predefined corpuses, it fine tunes itself on a very specific process knowledge. In this process, we saw that the model was able to handle uncertainty and risky situations like unsafe question generation. But most importantly, it comes back to ourselves asking this question at what went wrong in the input data? Why this large scale input data on which the model was trained on is not sufficiently enough to constrain the safety of your generated questions. Essentially, when we looked at it, we looked at the most important component of a labeled data set are the human annotations. And these human annotations in this very simple sense are not simply a one-day tasks. They involve the annotators to explore the experiences, the histories, look at the web search corpuses, and also look at expert guidelines. Some of our interactions with the clinical mental health care providers who are part of an annotation processes told us about the expert guidelines that they themselves refer to in doing the annotation tasks. But most importantly, such guidelines, such informations are not involved in the training of these models, and they are not even available at the output, so that they can be tested whether the outcome makes sense. Most importantly, if we all know about, even have a generative output and a classification output, they are a kind of a coalesced version of they are essentially coalesced form of one single outcome that tells whether it is a severity case of depression or it's not a severity case of depression. Whereas things are much more complicated than simply a binary classification. So we looked at that one possible way would be to utilize knowledge graphs. They are at a broad level, we call it information graph, assuming that we are talking about a more broader sense of information covering diverse and broader versions of knowledge graphs and lexicons. But one issue comes along with them is the amount of information that they're containing, and how do you identify a small subgraph within that knowledge graph that can actually help in the training of these deep learning, deep language models, and how do you use them at the output so that the model can verify its outcome. So what we looked at is we looked at various viable forms in which the knowledge can be infused, and the most importantly were this series of three information that we come up with. And these were the process knowledge, which talks about the structure of how a conversational system, I'm talking about in a conversational setting, how this system in a conversational setting can be utilized. For instance, how does a clinician interact with the user? How do they define their questions? What are the series of questions that they often ask? Coupled with concept net or a common sense information, because most of the time we are looking for the entities, and the entities are the information where the information is contained. Subsequently, you want to make it more domain specific. You want to utilize healthcare lexicons, like for depression, it is patient health questionnaire. For anxiety is a generative anxiety disorder, and for suicide, it is Columbia Suicide Severity Rating Scale. And but these forms of knowledge are another comes along with the various forms of knowledge that I would be interested to talk about more about it. But essentially, I just want to give you a high level view of how these knowledge graphs look like, and there are various ways they are being constructed. They are having a manual effort. They can be constructed automatically, or they can be constructed semi-automatically. But what we want to highlight in the today's tutorial altogether is about this process knowledge. There you can see on the screen on the left side is a process knowledge, is a questionnaire that that a clinician utilize to define the severity of the suicide of an individual. As you can see, there are asked questions 1 and 2. Then if those questions are being asked yes, then ask question 3, 4, 5, and 6 in sequence. And if they are not being answered, and then if the sixth question is not answered, then there are another series of labels that are associated with it. So if you can look at this complicated procedure of information and you can model it into a particular tree structure or a flow chart where you can say question number 1, 2 are in order, and every yes and no is contributing to a label. And you can check that whether these questions can be answered based on the user input or not. If they are answered, they are capable of answerable from the user's input, probably you will have a label associated for that particular user's post or user's response. And not only in suicide severity, you can also look at the anxiety. Now, the difference between anxiety and suicide related questionnaires is the structure. Now, there's definitely a flow chart in suicide, but that cannot be a flow chart in every other mental health conditions assessment. As you can see on the anxiety over here, there are the top levels are the numbers that will tell you that that's a percentage of confidence that the model have in answering question number 1, a given and user input. And the bottom point, 0.261, is the value that you're getting. That's the uncertainty that the model is not able to get a complete answer to that particular question. So essentially, by using the yes and no factor, which is a very native form of decision trees, naive-based algorithms, as well as the k-nearest neighbors, you can actually utilize them to make your classification more interpretable and safe in your as a component in your question in a conversational systems. And that's what we will be diving into this tutorial. So I want to give you a very initial preface of what's coming next in the tutorial, which is we'll talking about a broad range of algorithms that are being developed under the hood of knowledge-infused learning, which is a class of neurosymbolic AI essentially developed in a way to utilize lexical, domain-specific, common sense, and constraint-based knowledge to make the model interpretable and capable of generating user-level explanations. So essentially, what we are talking about today is how models can explore the duality of data and knowledge in their outcome generations. Starting with the first, which is a shallow infusion of process knowledge. Here we want to talk about the things that we are more excited about to share is how you can transform your data into a way that is driven by process knowledge. Essentially, what we are dealing with is we are converting a user post and the outcome that's not binary anymore, but rather a series of questions for which you have an answer yes and no. Essentially, a task of the model now is to come up with a series of outcomes that will tell me how many questions can be answered with a certain degree of certainty given this user's post, and how many of the questions are not answerable. And the questions which are not answerable are the ones which are contributing to the follow-up questions that the agent would be asking, rather than a random series of questions. So here the model is nudging how much of the information I can extract from the user's response, and how much of the information I need from the user in my subsequent conversations. And essentially, this is a very simple structure with a semantic embedding loss to identify the similarity between the outermost representation of the user's post and the representation of individual questions being matched, and checking whether there is an outcome of yes and no. Here, the user level explainability and safety is introduced by making the model check whether the questions whether the representation that the model is able to generate is similar to some of these questions. If it is not, then probably the generated subsequent questions that the model would generate probably would not be safe anymore. And we want to check that whether the model, when I was capable of answering yes or no to these questions, which are the phrases that does the model highlight, and that will contribute to the user level explainability, because that phrases you can map them to the questions in the PHQ-9. So this forms at the shallow infusion, where we are more interested in making a data set that is more driven by the process knowledge and forcing the model to follow this particular structure. In a semi-deep infusion structure processes, what we do is we stack the deep language models with an interpretable model like a decision tree. Now the decision tree is capable of, we all know that decision tree is a very is a good interpretable machine learning model, and is capable of generating a tree structure. And what essentially we are looking for is a tree that will tell us that which of the questions can be answered and which of the questions cannot be answered. Just like in the previous setting, but rather than having yes and no straight away, we want to formulate it as a tree in a tree structure. And we want to see that which of these questions the model seems to be seeing things that they need to be asked in a sequence, and a question that needs some divergence. And in this semi-deep infusion, the most essentially part is that we keep the data set as it is in the shallow infusion structure, but we make some amendments into the language models. Like for instance, stacking a decision tree over Ernie, stacking a decision tree over long formers, or any of the foundational deep language models. And this structure is introducing interpretability in the form of the decision tree, because if the model is not able to get the close representation of outcomes, it's back propagated to your decision tree for a much more richer structure of the decision trees, like more yeses and more of no. So it's kind of a nudge between how many questions can be answered with yes and how many questions can be answered with no. And you are able, and most important part that we looked into this structure is that it also gives you a capability to introduce the concept of annotators, agreements, and disagreements into this structure, which is also provided into our archive version, which talks about this process knowledge infusion in much more detail. The third form of knowledge infusion that, so in today's talk, we will be focusing specifically on shallow infusion and semi-deep infusion. And deep infusion structure is what we are right now exercising and constructing, which talks about that in a deep neural network, at every layer, we want to nudge that how much of the representation. So it's kind of look like a phenomenon of probing, where we want to check that at every layer, we want to check how much of the learned representation is able to get is able to answer certain questions in the clinical every of these questionnaire like SCID has some, like say 10 questions, for instance. How we want to check that how many of those out of those 10 questions, how many questions the model can answer from this learned representations. And if it can answer, let's say 5 questions, then 10 minus 5 is what we will be using as an modulating value for the hidden representation. And we want to also introduce a new representation for the remaining 5 questions that the model is not able to answer. Together will be a balanced balanced reward function that will be introduced in this model for this learning. And we want to check that the outcome remains the same as the tree structure with using the decision tree, and the backpropagation remains the same as the model. So with this, all this infusion of knowledge that I talked about today, what essentially are we looking for in terms of benefits? We are looking at a context-sensitive capture, because we know that the model, the statistical AI model as it stands right now, is completely driven by the input data without the information, without the help of an external knowledge, which is required to its more adaptation to the particular context of the user. We will be talking about the uncertainty and risk associated with this input and output, and how knowledge can help you in preventing from indulging into risky situations. We are we have been looking into the interpretability concept by introducing this process knowledge as a way of in the form of an interpretable machine learning models that can be stacked over to the over the deep language models for more interpretable classifications. And most importantly, we are looking for the user level explanations, which talks about how the system can generate explanations which are not simply identifying and highlighting phrases of attention, or which are being manifested in visualizing the attention matrices, but rather we are looking at how these identified phrases map to an existing questionnaires or existing knowledge that an end user can understand. And which, if we are able to achieve all these 4 points, we are able to move into a state where an AI model is task transferable across multiple tasks in a very complex domain like healthcare. So this summarizes our challenges that we identified in conversational agents. And the remaining part of the tutorial will highlight 3 major points, which are like the reinforcement learning, how it can be used in a cooperative multi-agent systems, and how does process knowledge integration happens in the reinforcement learning for conversational systems. And we'll come up with show you a demo of how this infusion actually makes a conversational agent much more safer than one which is not with the process knowledge. Now, with the next part of the tutorial, I hand over to Chi, who will be going over the reinforcement learning.
Yep. Can you see my screen and hear me?
Yes.
Okay, great. Yeah, hello, I'm Chi. I will be delivering the second part of this tutorial. As Manus briefly introduced, we have seen some brilliant examples of knowledge infusion in a general learning setting, specifically for the conversational agent. And our tutorial will highlight a specific learning framework called reinforcement learning that our group, our AI Institute, has been working on for a while. The reason that we want to sort of look into this, learning framework is because we found that in some applications of ours, this RL is the perfect, way of, looking at and modeling problem. So in the next few slides, I'm going to use roughly 10 to 15 minutes to sort of give you a very high level introduction of reinforcement learning in general. And after that, my partner, Kaushik, will be talking about knowledge-infused reinforcement learning, which means that in traditional RL or reinforcement learning, there will be some drawbacks or weaknesses that could be potentially be overcome by our knowledge infusion method. Okay. Right, let's get started. The first question I would like to answer is, what is RL? What is reinforcement learning? And I have checked a lot of definitions or textbook, and I would like to summarize what RL does in a simple sentence, which is RL essentially learns to make good sequences of decisions. Let's parse this sentence a little bit more carefully, right? So the last several words of the sentence is sequences of decisions, which is sort of more general than a one-shot or one-off decision making. For example, if we're doing image classification, we're selecting between whether this image is about a cat or a dog or nothing or neither, then this should be interpreted as a one-off or one-shot decision making, that there's nothing happens really after that, right? So either it's wrong or correct. But in many more other scenarios, such like robotic scenario or dialogue interactions, the agent or the system or the machine that we are designing are trying to make a sequence of decisions that is situated in some environment. Examples including, for example, if we're designing a robot, it has to make a lot of decisions about its locomotions in a sequence in order to make progress. That's the very first bullet of this definition of RL. The second aspect is that we don't want our agent or our system to make arbitrary sequences of decisions. It has to be good in some sense. And in the RL sense, this goodness or goodness metric is eventually going to be measured by this so-called reward signal. We have something called reward that measures the quality of the sequence of decisions that agent is making. But the third bullet, really reinforcement learning is a learning framework, which means in learning, the agent or the thing or the learner initially does not know something. And that thing is trying to hinder the learner from making good decisions. And through this repeated interactions with its external environment, the learner really learns something from the environment in order to make good decisions. The third bullet, or this word learn, really means there's no free lunch. You have to make some errors or failures in order to learn from, such that in the long term, the agent decision will be better and better. Okay, so it's kind of a one sentence definition of RL that I'm thinking is really faithfully explaining or describing what RL does. Really, the name of this framework, reinforcement learning, comes from really how we train animals, right? So we train animals with so-called reinforcement. It's essentially, for example, if you're training a dog, if the dog is doing something that you desire, you really feel this dog positive reinforcement, so that the dog knows that it is doing something really beneficial or rewarding, such that it will keep doing such kind of thing in the future. On the other side, if the dog is doing something wrong from the perspective of the trainer, then the trainer will give this dog some negative reinforcement, such like pain, hunger, essentially no food, and dog will learn from this punishment or negative reinforcement. So we're trying to essentially in the RL to do the same thing with machines. Just replace a dog with a machine dog, and let's train this kind of machine dog in a principled manner. That's essentially what RL does. So here in RL terms, such kind of reinforcement that is essentially what the dog or the learner is learning from. It's called reward signal. It essentially tells the learner what is desired and what's not. And we will call those machines reinforcement agents or simply agents. So really, what's underlying this framework is the reward signal, which is a critical concept in such a learning framework, and specifically or more rigorously, a reward is some scalar feedback. By scalar, we mean it's just a number, it's a real number that is happening, that is generated by our trainer, by the environment. Every time step t, there will be a reward generated, and which can be perceived by the agent. And the agent job, the dog's job, is to really try to maximize the cumulative reward, which is nothing but the sum of those reward over time. And RL is really based on this reward hypothesis. What essentially this reward signal does is that it tells, it describes the goal of our task. All goes in this, according to this hypothesis, it's just a hypothesis, it's controversial. All goals can be described by the maximization of this expected cumulative reward signal. We have some examples shown on this slide, really try to give you a flavor of how general this reward hypothesis, or how, to what extent this reward hypothesis is true, or how general this reward formulation is. Example, so the canonical example of RL, or just one of the canonical examples of AI is to, design a game player or game engine, for example, chess player. Then in these scenarios, the reward is closely related with the result of the game. The agent will get the plus reward if it wins the game at the end, or some minus reward if it loses the game at the end, right? So there will be no reward or zero reward in the middle of the game. If you define the reward such way, then the objective of winning the game, or maximizing the probability of winning the game, is equivalent to maximizing this reward system. And the second example, where we have this application of managing an investment portfolio, then this reward signal will be correlated with the number of dollars in your bank account. Similar thing happens with controlling, when you control PowerPoint, power station, or make some humanoid robot walk. So in this scenario, we can conceptualize some reward signal that characterizes what you want the agent to do. Okay, and then and I would like to introduce this RL loop diagram that's really explaining what's happening between the agent and its external environment. So every time step, the environment will give the agent some reward feedback, as well as the observation that the agent can make. And according to this reward signal and observation, and all the rewards and observations that happened in the history, the agent has to make its next decision, which we call it an action in RL. So this examples, including all the examples I've introduced, and importantly, we are highlighting this conversational agent in this tutorial. And the goal of the agent is to maximize the future reward, which means it may require sacrificing some intermediate reward to gain more long-term reward. This short-term versus long-term dilemma or a reasoning is one of the most challenging aspects of this problem. So two examples I want to really show. One is blood pressure control. In this example, the environment, which is essentially the patient's body, right? So the agent is the algorithm that decides what to do with the agent body in order to control its blood pressure, in order to make this the patient's blood pressure under control. So the observation here will be all available patient information that can be sort of monitored by some medical devices, right? So the reward is going to be positive if the pressure is within some healthy range, and negative otherwise, and negative for some side effects. An action will be either to recommend a particular kind of intervention for the patient. For conversational agent, the the agent will be the conversational agent we're developing. The environment is really the chatbot scenario where the chatbot is talking with some user. So the observation will be user utterance. Every round of conversation, the agent will observe some utterance from the user. The task, the reward will be corresponding to how the task is completed. If the agent is task oriented, for example, if you are booking a flight for the user, then the reward will be going to be related with how well this task is complicated, as well as some user satisfaction, metric that you could consider. The action in this scenario will be the very next utterance the agent want to make for the user. Okay. Right. So my last slide is this is my last. I really want to generalize this idea to the multi-agent setting. In some scenarios, you will have a lot of more than one agents either collaborating or competing with each other, or simply they're just coexisting with each other in some shared environment. In this scenario, I just want to use this one slide to illustrate what's happening here. So the environment will still generate some reward signal and observation signal, but it will generate such signal for every agent respectively. And every agent sort of has to take as input its own observation and reward in order to, as output, decide what its action that is going to be for the very next time step, right? So this joint action, the all agent action essentially will determine how the environment will transit at the very next, time step. Okay, just so any RL algorithm, including the knowledge-infused RL algorithm that we're going to introduce in the rest of this tutorial, will be trying to decide the outgoing error from the agent, how the agent is going to make the very next decision based on the previous information. Okay, yeah. With these slides, I'm concluding my talk. I'm going to transit to Kaushik on the specific scenario of knowledge-infused reinforcement. Thank you.
Can we ask questions? Can you hear us?
You're muted, Kaushik.
Yeah, I can hear.
I had a question about the multi-agent response. Was it intended that all N agents would propose utterances, but only one of them would be selected to show to the patient, or are there parallel patients too that respond to the utterances?
Well, yeah. So the multi-agent setting, we are not targeting this setting for the conversational agent scenario. Pretty much every conversational agent scenario that I have seen is all about a single agent. You just design a single agent that is communicating with the patient. But you can picture a future where it could be beneficial to include multiple chatbots co-organizing a conversation with the patient. That will be the true multi-agent setting for the chatbot scenario. But I'm just proposing this diagram or as a framework in case you need more than one agent to finish your stuff.
We're going to have the requirement for supporting multiple users for an agent. So in a classroom, school-based setting that we are looking at right now, let's say a social robot or a conversation agent is interacting with 2-3 students at a time in peer learning context. in that case, we will have to support more than one users. But that work has just started. Nothing has been really completed there. Kaushik?
Can everybody see my screen?
Yes, yes, I can see it.
Okay. So I will be talking about how knowledge can be incorporated into the reinforcement learning framework. So as Chi talked about, in reinforcement learning, essentially you take actions, interact with the environment, obtain reinforcement from their environment, and there's some state change that happens. And it comes of the policy to the knowledge that was relevant to deciding on that policy. So that allows for rich explanations that can be understood by the users of the system. And once the explanation is generated, it may show that there are some holes in the knowledge that was used, and subsequently the expert can be consulted and the knowledge can be updated. And this continues in a loop until we're satisfied with our learned policy.
Well, wait, what is the explanation of? It's an explanation of why the agent decided the policy,
Exactly, yeah.
and how do you, this is, okay, so in what form does it take? Is it as highlighted span of text?
So if it is a text-based thing, then it's a highlighted form of text. If it's symbolic knowledge, then it can be a logic rule or it can be a path on the knowledge graph.
And is this loop here, the reinforcement learning loop that we saw in the previous bit?
Mhm. Yeah, that loop is sort of collapsed into that knowledge-infused RL box. There's where the loop happens. The reward, that's why the bidirectional arrow between the data and that box. The reward is taken into account in the knowledge-infused RL algorithms. And actions with high rewards are encouraged and actions with low rewards are discouraged.
And finally, how do you calculate the explanation? Or is this high level that you don't tell us right now?
I will show you some examples.
Okay, okay. Thank you.
So we applied this architecture to adaptive contagion control. This was during when COVID was at its peak. And we designed a simulator of a region in and around New York based on CDC data of how people are behaving in different areas of the city. And the actions that they can take is travel to work or some other place or go on some particular highway. And then this is all publicly available data. And then how many hospital beds are available at the time, and things like that. So what we do is construct a feature representation from that information about the current state of the city or the region that we are inspecting. The reason we do that is because now we have to decide actions like in that city, what should we do? Should we lock down a particular sub-region or should we open it up or what should we do? Right. So, so we construct features about the region that we're inspecting. And then there is some external knowledge from experience with the pandemic so far. Like if there is high traffic on a particular region and people are aggregating at a stadium because of some game, then you'd like to lock down that place. Things like that, common sense knowledge like that, that is already available due to previous pandemics like SARS, and also newly learned knowledge from the COVID pandemic. So the algorithm specifically that's used is a policy gradient method. Then this takes the state representation and the external knowledge and results in a knowledge guided policy. And this knowledge guided policy looks something like this. So it's logical in format. So if in a particular state, there's a residential area and a shop in the same state, and a person lives in that home, lives in a particular home, and the home in the residential area is also in the same state, then you might want to lock down this residential area. So that's what a policy looks like. It is interpretable because there is a very clear description of what is being stated. So because we can write a clear description of what is being stated, it facilitates faster evaluation by domain experts. And that can mean that we may have to modify our simulator or knowledge. So, and that loop continues until we get high cumulative reward, which is the reinforcement learning objective, and also evaluator agreement, which is the person, set of people that this system is meant to assist. So I'll move on to another application, which is mental health chatbot. This is a high-level illustration. In the next few slides will be a high-level illustration of the schematic diagram for how this execution works. And then I'll show you a demo of the implemented system. So what happens first is that the patient, once they visit the care provider, there is provider notes written about them. And that provider notes is compiled as a user profile graph. And then there's clinical guidelines either obtained from textbooks or provided directly by the care provider. And that in conjunction with the knowledge graph triples is fed into the reinforcement learning algorithm, which learns at any time step t what kind of interaction should you have with the patient. So the examples of the kinds of interaction that you should have with the patient is appraisal, which means that you praise the patient for following the guidelines up to this time step t, or information gatherings, which can mean that the knowledge is incomplete, so it needs to solicit some information from the patient, or symptom check, which is just tracking how the symptoms are progressing as the patient seeks treatment. Health promotion safety is a fail-safe action in case the patient is interacting with the chatbot in a way that the chatbot cannot handle, then a safety trigger is to alert the care provider immediately. And reminding clarification is reminding them of either medication or other therapeutic measures that they recommend. And these are just an example of a few. There are more. So once the high-level task is chosen by the reinforcement learning framework, it has to be decomposed into operational dialogue. So in a knowledge graph, along with the triples, there's also a schema. So using that schema, a dialogue generation module, which can either be template-based, which is rule-based, or a large language model, will generate the dialogue pertaining to filling up that schema, all the question marks in the schema. And subsequently, the user profile graph is updated. And this continues. So now I'll show a demo. So this is conversation between the system GPT-2 and a patient. So the GPT-2 bot asks, do you feel nervous? The patient says more than half the day. And these are the questions that GPT-2 generates. Do you feel irritated or distracted? Do you feel something extreme might happen? Are you able to relax? The third question is okay, but the first two is not something the patient would be comfortable speaking about with words like distracted and extreme. And that's why clinicians don't ask this. We didn't decide that these questions are harmful or negative. The clinician input with our collaborators, they told us that these are harmful. So to fix that problem, we asked them that how would they do it? And computationally, we model this as process knowledge, as Manas alluded to before. So what happens, this, for example, is an example of process knowledge for diagnosing depression. These are a set of 9 questions that the clinician needs elaboration on when they're conversating with the patient to diagnose depression. So when we incorporate this into the model, we see that the question 8 is triggered, which is related to being fidgety and restless, and questions related to that are asked, and without using harmful words. So like destructive or extreme. And these are medically better questions, better follow-up questions than what GPT-2 generates. Now we'll move on to the example of how to detect if they have suicidal tendencies. So when the bot asks what is going on with you, the patient responds with something quite hairy. Yes. This is quite alarming, a response. I have a gun, I'm not on a ledge or something, but I have a gun on my lap. So GPT-2 is generating questions like, a gun sounds alarming, what is on your mind, which is fine. But the last two is really inappropriate. So once you incorporate the clinical question that the clinician actually uses, the responses are much more tame and controlled.
How are you identifying automatically that the responses are inappropriate? Is it just a keyword match, or is there some sort of a similarity?
It's a similarity, and then a qualitative evaluation by the expert.
No, I mean, in general, it has to be done at a semantic level, and that's where our use of knowledge graph is what would enable that, right? Nothing we want to do is going to be.
The joke you want about a law. Like, how do you identify that that's inappropriate at training time? Not a human. Like, how does the system identify?
what is inappropriate is told to us by the medical expert. So that is annotation given to us when we generate.
That's the label, but that's the label, but how do you, when training the model, how do you identify that?
So I think the reinforcement learning process, it's not given a reward, would be my guess.
Yes, that's true. So if it is in the label a negative generated sentence, if it's similar to a negative generated sentence in the ground truth, then it will be given a negative.
I thought they were replacing the inappropriate response with a better response in the process of choosing a better response.
Yeah, these
After
are two.
eliminating that one because it was inappropriate. They haven't shown it yet to the patient.
So that's on the test side. On the training side, you would already have those. It might be a different conversation altogether. But the model is trained to kind of identify those conversations more. And when you come to test, you similarly see those that particular policy in place, so the behavior is also. Again, I shouldn't be speaking, but I think that's what we have.
Thank you.
Okay, so the first question, it says question 1 here. What it actually tries to answer is wish to be dead, and then that the model finds out the answer to that is yes. And then there is the second question is non-specific active suicidal thoughts, which again the model finds the answer is yes. And the third question, 4th and 5th, are all related to, as well as 6th is related to active suicidal ideation with some intent to act. So then finally, the model decides that this person's suicidal tendency is at level behavior or attempt. And the care provider is alerted immediately with the tag urgent. Now, from the provider notes, after the care provider
I'll just note here that this is a technical thing. We have not figured out the legal implication of our being able to do this. What if we make a mistake in identification? That will be a big liability. So I have this is with a caveat that technically, it's very important that there is a notion of safety that should come in as conversational agents go more into important, and challenging topics of personal health and other interests. But there will be things that are not, solved. They will be solved just the same way in autonomous vehicle are on the road, even though they can kill people. The same thing will hopefully figure out, but that has not been fully figured out.
Right. So here, after the provider is alerted, the patient sees the provider, and now there's a new set of provider notes. And the provider note mentions that the user takes ziprasidone and also that the patient has depression. So the bot knows that depression is a medical treatment for depression is the drug fluoxetine, or commonly known as Prozac, from its knowledge graph. Then once the patient answers in the affirmative, that is added to the patient knowledge. Now, the bot, like I said before, has knowledge about fluoxetine. It gathers that knowledge from its external knowledge graph, that it is an antidepressant, it belongs to SSRI class. It works by increasing the chemical serotonin. It's used for depression treatment, and it is available only by prescription. So using this information, the bot asks, have they prescribed you enough refills? Because it is able to ask this question because it knows that fluoxetine is available only by prescription. The patient responds with, it's not helping. And now the bot knows that fluoxetine counteracts ziprasidone. And so it devises a hypothesis and alerts the provider of this, that it's possible that it's not helping because the patient is taking ziprasidone. Now, continuing the conversation, the bot also has from its external knowledge side effects of fluxity. So fluxity can affect hives, skin rashes, restlessness, fever, and irregular heartbeat. So the patient confirms one of these symptoms, which is that they're having trouble sleeping and they feel their heartbeat is strange. So the bot with an urgent notice alerts the care provider of possible interaction with ziprasidone causing irregular heartbeat. And then the care provider contacts the patient, and there's a new provider notes now that the user needs to exercise at least 5 days a week. Using this information, the bot confirms if the user has indeed followed that course of therapy. And they respond once again in the affirmative, and then the bot appraises them for it. So this is a demo of, this concludes the demo. So I said that explanations are also part of it. So let me show you some examples of the explanation. So from the knowledge graph and from definitions from the DSM-5, you can get explanations of the following sort. From a patient's text and the phrases that have high attention in the neural network, you can connect that to different classes in the SNOMED city knowledge graph. So these correspond to concepts that a clinical expert can understand, because this is built by clinical experts. And also using the phrases, the definition from the DSM-5 confirms that a potential diagnosis, potentially likely diagnosis for this excerpt of text is obsessive compulsive personality disorder. This kind of explanation is much more useful to the expert than if all this was not there and just those highlights were present, which is what attention visualization does. How does process knowledge help a user level explanation? Essentially, it highlights the path that led to a particular outcome. What that looks like is this. It highlights the sentence or sentences that led to answering specific questions. And that way the clinician can trace the exact path in the flowchart that led to that particular outcome. Using this method for a mental health domain data set, our model outcomes, the experts agreed with 70% of the time. Our best baseline model was ExcelNet. It's a large autoregressive language model, and that achieved an accuracy of 47%. This is what the program actually outputs. This was an illustrative example. It outputs an explanation of yes and no for each question in the CSSRS data. With that, I'll hand it over to Manas to talk about conversational information seeking.
Manas, it is 4:15, so let's keep that in mind.
Sure. So following up with what Kaushik talked about on the knowledge-infused reinforcement learning, where there's a multi-turn conversations between the user, between the patient and the doctor, I want to talk about a very separate but very parallel use case of an agent where we exercised that is it really necessary for an agent to converse in a multi-turn fashion? What if the agent is capable of generating questions in sequence and letting the user interact with the system to say which of these questions are relevant, and you get a cohesive and accumulated response? And this comes down to the problem of conversational information seeking. This is a very fascinating and an emerging area within the reinforcement learning paradigm and conversational AI that attempts to develop systems that would allow them to initiate a conversation with the user. And essentially, the idea of conversational information seeking comes from the very nature of human information seeking behavior, which has a particular structure. And human information seeking behavior involves a covering of an object, a particular topic in a very detail, expanding on the breadth of the topics as well. So essentially, what I found was the three major criteria in which the human information seeking behavior can be manifested. The one is task oriented, and it's like, for example, a person is seeking information about preparing a delicious cuisine, or he's asking information about health conditions. Essentially, what Kaushik talked about was when a agent would learn to interact with you over time. Here we are looking at a system which can itself has a capability of generating questions which are contextual, lexical, and syntactically diverse. And most importantly, they are related to each other and they have a particular structure in which they can be asked. The most benefit of having such a type of question generation is in shaping of the response. You want the model to understand that these procedural questions keep track of the entities and actions, and which are the questions which are relevant to the user, a cohesive response is delivered to the user. So these forms a major concept that drive our next structure within the reinforcement learning, most importantly, the knowledge-infused reinforcement learning called ISEEK, where we say we are looking forward to develop an agent that can, or we are asking ourselves, is it possible to develop an agent that can mimic humans' information seeking behavior? And essentially, this forms a new paradigm within clarifying question agents and follow-up question agents, which try to ask you the same question, having the same entity as the user queries, which kind of misses out the engaging flavor that a conversation agents need to have. And what essentially we are doing with ISEEK is, for every query that you are providing, or very information that you're asking a user, an agent, it asks you a series of questions. And those series of questions that it asks you, you pick which of them are as a potential question to get your response. Or if you can, it's an information seeking question from the agent, you provide a particular response, and it will ask you it will give you a more cohesive response than rather than simply doing a multi-turn conversations, which kind of being very long and it might not reach to the topic. So when we looked at this application into a very generic use case, definitely mental health care is one of the complicated use case, but we want to test out whether the system works in a very generic use case. So we took baseline T5 model, which is another very much larger than ExcelNet in a generative scenario, and we wanted to interact with the user. And the user's question was that the user wanted to learn about blockchain relationships into cryptocurrencies and their importance. And if you can see the questions that are generated by the model, the last question, which talks about, do you want to know blockchain in currencies? The most important thing is that blockchain is related to cryptocurrencies and not currencies in general. So that's kind of an irrelevant question being generated. And most importantly, the idea that when we looked into this reason why this thing happened, it's mostly because cryptocurrencies were broken into crypto and currencies, and which loses the semantics between currencies and cryptocurrencies. Another point that we found that without presence of external knowledge, the model is vulnerable to more redundant question generations, and it minimizes on the diversity in the question generation phase, because the most it does not have external knowledge, it does not have external support of how it can generate better questions, and what it can totally rely on is a user provided query. In the ISEEK, on the other hand, it kind of create a small common sense graph along the entities that are being given by the user query to construct a more cohesive graph in a form that can drive your question generation processes. A series of questions are generated, and this is what is being asked to the user. And it also tells two things. One, whether the agent is going in the direction where the user wants, and second is if the agent is going in the right direction, whether the questions generated are related to the query, or they are completely divergent from the user queries. So an example of this scenario in action was that given a user query which talks about economy and employment statistics, it talks about a bunch of keywords on economic concept, GDP, inflations, and influence of employment. And essentially what model does is that it takes a very state-of-the-art constituency parsing method, which is pretty much used in the natural language community. It identifies a series of phrases, and what essentially do is that it looks for these information in a concept net graph. So we use concept net in a very simple sense because it is multilingual. We are looking for a query that can come up with any language. And essentially we want to come up with this small graph. The task would be to utilize this graph, and you traverse it from a root node to the leaf node to the root, sorry, from the leaf node to the root node, and you create various versions, various expansions of this user query. So given a simple query, you create a various different illustrations of this user query, like income tax, income, cost living, inflation, and economics, or you can talk about unemployment and inflation and then economics. So you kind of look at these kind of subject, predicate, and object triples to be a form of an expanded version of the input user query. Essentially, the task would be to generate a representation of these triples and utilize a kind of a dense passage retriever, which is you can actually look at online as well. But the dense passage retriever is an approach that has been recently developed with the Facebook AI research, which utilizes embeddings of your queries to be used in retrieving the passages. So rather than retrieving the passages by the token or word matches, you're retrieving the passages by the embeddings, by the numerical representations. So once you have these passages retrieved and ranked, now you have the passages and you have these expanded queries. You pass them both to a sentence BERT encoder. And for a simplicity, I considered triples to be sentences because they are subject, predicate, and object forms. And essentially what you do is that you pass them through a reinforcement learning paradigm. And essentially the task of this reinforcement learning paradigm is to generate these questions. And the most important fascinating factor that we looked at it was some of the questions that were generated were not even present in the user query. And these questions came up because we introduced this query subgraph. And there are various variants in which these questions are coming. And most importantly, sometimes what happened is that these questions do not come up to the top 10 questions, because as I said, a statistically driven model would not consider, will only focus on the terms that are present in the user query. So that's why you need a reinforcement learning paradigm, which tries to say that you want to diversify your question generation processes. So how do we seek such an improvement in ISEEK? Is that if you have if we took a baseline generator model, the T5, we gave us a user query on it about a person bothered, feeling hopeless and depressed, and the questions what it was generated was, are you feeling depressed, are you feeling bothered, or do you feel depressed? So if you look at these questions do not have any logical order. They share some semantic relations with the user query, but they are more redundant they're more redundant towards the user query, very specific on the terms that are being present in the user queries. So let's say, how about we introduce a neural passage retriever? Let's give this generator a set of passages that are very contextual, that talks about hopelessness, depressed, and maybe this set of passages, maybe some user post that are providing some functional or some active information on how a person can cope up with the hopelessness and depression. And the idea was, now this generator is fine-tuned on these contextually related passages, and you use it to generate the questions. Now, this model generates the question now much better than the previous one, but some of these questions that are generated, which are highlighted in purple, are unsafe. We call it unsafe questions, as I said, because we had a safety lexicon. This safety lexicons are a bunch of terms being extracted from healthcare questionnaires to identify that whether these questions are safe if the terms that are very similar to these terms, they are safe questions, they are safe questions or safe sentences. And if they are not similar to these terms, then they are not safe questions. Essentially, you are able to capture the context. You are talking about the terms very similar to the user's post, but definitely you are unsafe, but you are able to capture the context. You also brought in some diversity in the question generation, but the semantic relationships with the user query and the logical order is still missing. Now, when I say semantic relations, like how often these questions are very targeted to the user query. A user do not want an agent to keep on asking the same question that are very surrounded between the terms or the entities that the user is providing. So what we introduced in the concept over here is that a kind of a query knowledge graph, a subquery graph. I kind of showed it as a form of a common sense knowledge graph, but it's kind of utilizing the common sense knowledge graph to construct a small query subgraph, which I illustrated in the previous example. Now, the task of this query subgraph is to bring a diversification in the question generation. For instance, if I have depressed, depression is a common term that is being associated with depressed. So definitely depression and depressed are relatable terms. Hopeless and hopelessness are relatable terms. And subsequently, sadness is also very similar to hopelessness or hopelessness. So here what you're trying to say, you're trying to develop a kind of a system that can bring in more diversified terms in its question generation, and rather being very focused on the terms and the entities. But most importantly, what we wanted to show over here is that it tries to expand its knowledge across various terms that the user might not able to cover in his user query. But the order in these questions are not there. And you know what? The logical order you cannot introduce using knowledge graphs. You cannot introduce using a generator. You need a discriminator, a model that can enforce this logical order. What can knowledge graph do is give you more diversified context in the generation processes. So that brings us to the final stage of the IC variant, where we introduce an evaluator. The evaluator tells me that if the current question and the previous question have an entailment relationship, entailment, neutral, and contradictory are the three major classes within the natural language inference domain, which tells you that the two questions entail each other, or if the two questions are neutral. If they are neutral, that means they are communicating the same information. Or are the two questions contradictory to each other? So you probably do not want a contradictory question to be generated. And certainly you do not want the redundant questions to be generated. You want questions that are entailment with each other. So that's what an enforcement is, what we are bringing into the generator. And that is being introduced using a trained evaluator on questions that are being in order. And if you see questions that are in order are the ones which are in the PHQ9, GAD7, CSSRS, and you can have all series of questions. So what we did was, this is something that I kind of missed in the previous slide. How do we train and evaluate a network? So what we did was we took PHQ9, CSSRS, and GAD7, all those questionnaires. For every question of those questions, we looked at Microsoft Bing API and Google SERP API to retrieve people also ask questions. We kind of utilized those. We took those questions, filter out those questions which are not semantically, which are not safe. That means they had terms which are, because we are looking at online, we are looking at the web. The questions can be of any form. We want to look at it into the specific. We are looking at the specific questions that are very safe, and we constructed these data sets. And that's where we train and evaluate a network which tells which are the questions that are relevant and which are the questions are not relevant. The irrelevant pairs of questions are the ones which we term as adversary, and the questions which are good are the generative questions. So that's why we call it generative adversarial reinforcement learning system. So with this, I want to move on to give the screen to Dr. Sheth, who will be talking about the summary and the future directions, which summarizes where we are right now with the knowledge-infused reinforcement learning, and what are the immediate research directions that Artificial Intelligence Institute is going to explore in the domain of mental health care.
I'll take only a couple of minutes as we are more or less out of time. Manas, there are a couple of questions waiting if you can address, and you need to project my slide because I don't have slides.
Okay.
So one of the very interesting thing in front of us is how do you build a system that supports both system 1 and system 2. And we feel that, I mean, we've done amazing work with, community has done great work with statistical AI and learning from data. But much of what you see as the limitations, such as inability to provide user level explainability, is because the systems does not make use of knowledge. And knowledge, we just explored some of the types of knowledge. There's so many types of knowledge that are available: lexical knowledge, knowledge in dictionaries, knowledge in manuals like DSM-5, and process knowledge as in questionnaire. So we humans use this all the time, and the AI system need to be able to use them to become more useful for humans and to be able to do more advanced work, such as do the simpler aspects of mental health triaging or support. Not necessarily, we are not ready to do very complex aspects of mental health, let's say, but some of the things, routine aspects, for example, on self-management can be done by the AI system. But even for that, and even for users to have trust in the system, we would need things like explainability. We will need things like making interactions safe with AI systems, and and for that, knowledge will be important. I put in the chat a link to a very broad article on the variety of forms of knowledge that is necessary to build a system that is more humanist. And the other thing is that we built a system that are well for working for one modality, but humans are multimodal. We listen, we watch, we talk at the same time. So we are building systems where we use data of different modalities are understood at a higher abstraction level, and then we are doing more semantic integration. So that is a general. So here, for example, autism is a very complex disease, and 50% of the people are neurodiverse. Social issues and many other things, people vary. Language skills, people vary. So we are interested in building the systems that are more attuned to individualize or personalize the solution that deal with humans with different capabilities in different environments. So that is another major things that the thing that we're looking at. A very powerful concept is personalized knowledge graph. We had introduced the concept of personalized health knowledge graph in 2018, and that was expanded to personalized knowledge graph by Google guys and others. But that is a powerful concept where system keeps track of all the interaction with the human, has longitudinal understanding, and then uses that to tailor the interaction with the human. I think that's what this thing is about. And yeah, there's this thing about user level of explanation. I think we already talked about it, so I'm going to pass that. Anything else that we have left, Mars? Yeah, okay. And there's some references that you can get from the slides. We can take any questions if you have. So reach out to Manas if you have questions that were not yet answered. And
to wrap up, I just wanted to share with you all that we have an extensive series of data sets that we have built at the AI Institute, which we call under the umbrella of knowledge-intensive language understandings. They are publicly available data sets, but we kind of control them in the form of that you kind of have to fill up small, either email us with an example, with an illustration of why you need such data sets. But we have extensive series of data sets on mental health care that extensively utilize knowledge graphs in achieving state-of-the-art performances. And we have discussed these data sets along in various venues of in AI conferences. And if you have any questions along these along the tutorial, feel free to email me. I will happy to answer any questions which are like even subjective questions and even queries requesting for the data sets.
Thank you.
The data is you might call open source accessible. That's I'm answering a question by Dan. The code is not yet open source, I believe, right? Manas, have we done any open source open source of codes?
So the data set is open source, codes and everything. If you can send us an email, we'll happy to share the repo for the codes as well. So Ankit's question is about language model is being used to generate questions, and reinforcement learning is choosing or replacing questions. So the reinforcement learning is learning to not so it's giving you so in the conversation information seeking domain, the ISIC model is learning to replace the questions. It's not choosing the questions. It's however, in the context of mental health space, which Kaushik talked about, where you are talking about self-appraisal and a more close environment of interactions, that's where the model is choosing to ask the right questions as opposed to replacing it. So these are two variants of knowledge-infused reinforcement learning.
But these are not the systems like open-ended conversation that a standard chatbot will be engaged in. These are the systems that need to be in confine of the particular medical discipline. So if you can't simply type in a question and a large language model GPT-2 or 3 giving you the answer and then goes, no, the reinforcement learning was used to pick the question to be or to the conversation, the next thing to pick what should be asked and to control that. And general idea is the following: imagine that you are going to see a mental health professional for some issue. Then the mental health professional uses his training and the mental health guideline that they are supposed to use for diagnosis or treatment. So the question interaction with the professional is being done with respect to their training and guideline, such as the one that will be found in DSM-5. And so we are trying to mimic that kind of environment. You don't have a large language model would not have the knowledge of that specific domain coming from DSM-5, and it will not be restricting its behavior to the domain knowledge such as the one that is in DSM-5 for mental health. And hence this is a different beast, and this is why large language models fail and are not appropriate for this kind of domains. Okay.
Any other questions?
In that case, we'll take the leave. Thank you very much.
Thank you everyone for the engaging conversations. It was really nice to have such an engagement. And if you have any questions, feel free to email us at my email is already there in the chat. Thank you.
Thank you.